Welcome back. It's time for special relativity. I'm not going to go over too much of the theory because I think you should actually just read it. And at the very least, there's a couple of videos that you should watch, YouTube videos that I think, with the production quality that went into them, they do a much better job than I ever will in this little video lesson. So I'd recommend going to the main class website. You can find it on May 21st on the calendar. And I would go to the crash course video and the physics girl video. If you watch both of those, that gives you a pretty good idea of a lot of the theory involved. It's not all the theory involved, but you can watch all the other videos if you want. I threw a bunch of the videos on there because they each say something slightly different. But if you're just going to watch two, I would say watch these two. It's not a bad idea to watch them all. You'll hear repeated information. The more times you hear something, the easier time you'll have for remembering it. But yeah, they go over the theory fairly decently. But otherwise, there's a textbook chapter that I put on there. It's a couple of pages long. I can't remember how many pages long it is, but it's worth going through and giving a read. It makes a lot of sense if you actually go through it. Okay, so without further ado, special relativity. Back in 1905, Einstein published a handful of papers that basically put physics on its head. I won't go into those details. Most of those videos will mention them casually, but otherwise, you should probably just even look up Einstein and go over his biography. He's a very interesting man. But lucky for us, special relativity only has two postulates. Postulate one, all laws of nature are the same in all uniformly moving reference frames. And two, the speed of light is a constant, independent of the motion of light of the light source or the observer. So basically, everyone will measure the speed of light going the exact same speed regardless of their frames of references. So special relativity pretty much exists because Einstein sort of pointed out some mistakes with basically what Newton came up with his laws of motion. And they didn't account for, well, what happens if you travel at speeds near the speed of light. And so this is the special case of when you're traveling at speeds near the speed of light, when your acceleration is zero. So special relativity deals with this case where you have no acceleration. You're in a frame of inertia. Okay, so these are the two postulates that go along with it. So essentially, what went wrong with Newton compared to Einstein, Newton's theories on motion were really good for the large objects that travel fairly slowly. Because at that point, the difference that happens with special relativity is pretty much minimal and immeasurable. So we tend to not really notice it or really care about the effects of special relativity. But when it comes to starting to go approach speeds at speeds near light, we have to account for that. And so one thing that Einstein discovered as a consequence is that not only is velocity relative, um, but because of that, time is relative, and so is distance. Because velocity is relative when it comes to your relative speed, if you will, driving your automobile, driving your car down the highway versus the car next to you. Right? If you're going down the highway going 110 kilometers an hour and it's single lane highway, someone's coming back in the exact opposite direction, going the exact same speed, you would probably consider yourself to be at rest, and the car coming towards you, you could easily say is going 220 kilometers per hour. And you wouldn't be wrong about that because according to your frame of reference, that is true. So if everyone's going to measure the speed of light to be exactly the same, and we're talking about speed as the speed of light as our universal truth that everyone's going to measure it the exact same, then time has to be relative, and so does distance. And that's basically where life got pretty complicated. So that also means simultaneous events may not actually be simultaneous events. And so that has its own consequences, which, again, I recommend you watch those videos to kind of walk through the theory. I'm just going to kind of go through the math with you guys. But if you understood that nonsense that I just went through, then you're probably pretty decent for now. So we'll go over this part of the theory when it comes to how this time dilation occurred. So Einstein did a lot of thought experiments. He was an experimentalist. He did everything in his head, and he thought in pictures. And so he came up with this thought experiment, the Gedanken experiment. So Gedanken's kind of a word that you'll find a lot. It's just German for thought. Sounds fancy if I say Gedanken. I know I pronounce it wrong anyways. I'm not German. So imagine yourself in one of two positions. You're either a person watching a train going to the right, or you're the person inside the train going to the right. So with two different frames of reference. Einstein thought of this thing known as a light clock. And that would suggest that, okay, so let's just call this person inside the train Alice, and there's a mirror above her, and she just shines a beam of light going straight up. According to her frame of reference, she's at rest. She'll see this beam of light go straight up and then reflect, go straight back down, and just follow this red path. We'll call this guy Bob, and what Bob will observe is as this light is going up and down the red path, it's actually going to the right as well. And so the path that Bob will see is basically this triangular shape. And so the distance the light travels, according to Bob, is going to be greater than the distance the light travels according to Alice. Because of course, this would be the hypotenuse of a triangle. So Bob sees this, Alice just sees the vertical part. So right away, we have a discrepancy. And we know that if the train is traveling to the right, it's traveling with the speed v, and it's going to pass a certain time delta t. According to Alice, it's traveling just this distance going vertical d. And Alice is going to have a completely different time, which we're going to call tau. So basically, Greek letter looks like the letter T. It's just a little bit fancier. So if we put them together, right, we're just showing Bob's point of reference. As the beam of light travels to the top and then goes back down, it's going to travel, if we just look at half the triangle, it's just going to travel at, sorry, brain died. It's going to travel the distance x. And if we're only looking at half the total distance, then therefore we're just going to divide it by the total time by 2. Whereas with Alice, the beam of light is just going straight up. We're going to ignore the fact that it comes back down. And so the distance the light travels is just going to be the total time, according to her, times the speed of light, because let's face it, we are talking about the speed of light, divided by 2 just for that whole reference there. And then to get the actual length that Bob would have measured, it's just going to be a matter of Pythagorean theorem. So if you factor in Pythagorean theorem, so that'd be this length here. So Pythagorean theorem, which would be, a squared plus b squared is equal to c squared. Here's our c squared, but have to be careful with calling it c because now c has a different meaning. C is, of course, the speed of light. Bob would see the speed of light going up at an angle. And so, of course, his speed would be c times the time that he's measuring divided by 2, because again, we're not going all the way back. We're assuming that the total tick-tock of the light clock, the total time would be all the way there, all the way back. So that's why we're dividing it by 2. So if you do some quick Pythagorean theorem with all the appropriate substitutions, and if you were to solve for just delta t, you got 2 choices. I can walk you through it, or I can just show you what it's going to be. To save 10 minutes, I'm just going to show you what it's going to be, because that's the kind of guy that I am. So essentially, if you solve for your delta t, you're going to get this horribly ugly equation. So this is known as the time dilation equation. So the time dilation equation gives you a person at rest, so bunny ears, quotation marks, at rest. So this is relative to Earth. We're assuming that you're standing on the ground next to a tree. Trees can't move, so therefore that's the reference frame that we're going to give this guy for delta t. This is the at-rest reference frame. Delta tau, that is going to be the in motion reference frame. Now again, that's relative because according to Alice, Alice is at rest and it's Bob that's actually moving. So you can actually interchange where Bob and Alice is depending on their points of view. So that's one of the reasons why special relativity gets really complicated, because it's hard to tell you with certainty and where you'll be right 100% of the time which delta t, delta tau goes where. So it all depends on who you decide is going to be at rest. So for the moment, Bob's at rest. This is the time that he measures. Alice is in motion, so according to Bob, so this will be her time, delta tau. V would be the velocity of the actual train, so the moving clock, if you will. So this here is the speed of which this clock is moving. So V is how fast Alice is moving, which is the train at this point. So that's the time dilation equation. So very often you'll see it also written down like this, where your delta t is equal to this gamma coefficient times delta tau. So this is the rocket frame, is what I like to call it. So this gamma is known as the relativistic factor. When it comes to special relativity, you're going to see this relativistic factor show up in pretty much every equation. So therefore, it's just put off to the side. It's like, okay, we're just going to call this its own little constant. This thing's actually known as the Lorentz transformation, which you'll probably learn about a bit more detail in some more advanced math classes as you guys further along your educational careers. So for now, you can just kind of call it the relativistic factor. So it's something that's going to come up quite a bit. And again, the hardest part is going to be keeping straight which one's delta tau and which one is delta t. Speed of light, on the other hand, that's just 3 times 10 to the 8 meters per second. That's just something I expect you guys to memorize. So I'll do a couple questions. Suppose the clock flies by us going 78% the speed of light. So very often you're going to see for these problems, you're not going to be given values that have the units meters per second. You're just going to get a percentage of the speed of light written down in decimal form. So 0.780 C basically means traveling at 78% the speed of light. So how much time will it take the moving clock to register 60 seconds? So the next hard part, which t versus delta tau is going to be the 60 seconds. So we're looking for how much time the moving clock is going to register 60 seconds. So that tells us the clock that's in motion is going to be tau. All right, so reading these questions and deciphering them will kind of be hard and tricky at times. Odds are good. If you do the problems and you are certain you did all your math correct, but for some reason the answer is wrong, odds are pretty good you might have just picked the wrong delta time factor, as and you probably just got those two backwards. So that's my first little heads up. So the next, your 0.78 times the speed of light, you can convert it if you really want to. I'd recommend not. Right? If it's given to you as a percentage of the speed of light, I wouldn't bother converting it like I just did here. I'm only doing this once in this video and the next video that I'm going to make. Generally, I would just leave it as 0.78 C, and you'll see why in half a moment. So I'm going to solve the gamma factor separately and then plug that into your time dilation equation. And you'll see real quick why I would never usually convert this 0.78 C into an actual meter per second. Because as soon as you actually plug it into the gamma factor, the relativistic factor, so V squared over C squared is the same thing as saying V over C quantity square. As soon as you factor in that 78% of the speed of light, you can see that the C divided by C, those will cancel out. And you just basically have your 0.78 squared. So if it's given to you in this form, keep it in that form. Don't convert it into meters per second. You're just creating more work for yourself. Then just a matter of plugging them in, square the 0.78, you should get this, 1 minus that, take the square root and then invert it, and you should get almost 1.6. All right, so that's just calculator math. You can do that. Once you plug that into your time dilation equation, you know that the clock that is moving at 78% of the speed of light has registered 1 minute, so 60 seconds. How much time would you measure that to be? So you would punch that through roughly 1.6 times 60 seconds is going to give you about 1 minute and 36 seconds. So that means time is moving slower for the person that is traveling at speeds near the speed of light. Right? They wouldn't see it that way because, again, from their point of view, their reference frame, they're the ones that are at rest, and you're the one that's actually moving at 78% of the speed of light. But if we're looking at your reference frame, Bob's reference frame, who's sitting by a tree or a building, something that we know can't move, their time would be the one that's actually ticking by a lot faster. And so that creates a bit of a paradox. And there's a big famous paradox twin experiment, thought experiment, which I think I should direct you over to the Physics Girls YouTube video. You should watch that one. I'm not going to put a little link anywhere here. It's at the start of the video. Just go to that. She'll explain what's going on there as far as how that can be solved. So, yeah. If you're at rest, you're going to measure something longer than the person that's moving. So let's kind of flip that around and say, same basic question, clock flies by us at 0.78% of the speed of light. So same question, almost. When a clock in our reference frame has registered 60 seconds, so now we're the ones at rest, right? We know we're at rest, we're next to a tree or a building or whatever, we're not the ones moving, we're in the earth frame. If we measure 60 seconds, 1 minute, how much time will, let's say, Alice, who's in the ship flying at this speed, how much time will she measure? So remember, time ticks slower for her if she is moving at speeds near the speed of light. So basically, the question does start off mostly the same, with the exception of now our delta t is going to be 60 because we want to know what the time registered on the clock that's actually moving is going to be. So that's what the delta tau is, the clock that's actually moving. So did this already. I'm just copying and paste that from a few screens ago. So we know at 78% of the speed of light, your gamma factor is going to be almost 1.6. So now when you take your time dilation equation and manipulate it to solve for delta tau, so in other words, you divide by your gamma factor. Very often, if I know I'm not about to do another question that's very similar, I would probably just combine these two equations and just do it all at once. So for instance, I would have just put this gamma factor 1 over the square root of 1 minus v square over c square. And as soon as I divide by gamma, this denominator actually becomes the numerator in this circumstance. So I just plug all my numbers into there. But since this is kind of like part 2, I already know that this is already 1.6. So I'll just plug it into my equation. 60 seconds divided by almost 1.6 will give me about 37.5 seconds. So in other words, Alice, who's moving at 78% of the speed of light, she would actually register 37.5 seconds for every 60 seconds that we would measure, assuming we are with Bob and at rest on Earth somewhere. So again, time is going slower when you're traveling at speeds near the speed of light. So when it comes to relativistic factors, we really have to take into account for special relativity when we start traveling at speeds near the speed of light. We can more or less ignore that. So all Einstein really did was he turned Newtonian mechanics a little on its head because, you know, the whole notion that time is no longer universal is kind of weird and crazy. But one of the main reasons it wasn't really noticed for for a couple hundred years is the fact that even if you're going at 10% of the speed of light, which we still haven't been able to do with, you know, vessels that humans can travel in. We can make particles go ridiculously fast, right? Almost speeds near the speed of light, but we can't make something that we could drive go even 10% of the speed of light. So even at 10% of the speed of light, what does the relativistic factor, the gamma factor, right? If you multiply any number by 1.005, you're not really going to change that number by too much. Right, so it's not going to change too significantly. So even at 10% of the speed of light, in most circumstances, you can kind of ignore the relativistic factor. But once you get into speeds like 50% of the speed of light, 70% of the speed of light, 90% of the speed of light, you can see how it goes up exponentially. And that's why very often when we're talking about accelerating things to speeds near the speed of light, you'll never hear a scientist say, like at the Canadian Light Source, oh, we can make our electrons go the speed of light. No, they're always very specific about that. We can make an electron go, what have I heard? 0.999996 is usually the number I hear. I don't know if that's right or not, but that's often the number I hear, times the speed of light. And you can see how that changes your relativistic factor as you go from, like for instance, 99.99% of the speed of light versus 99.999% of the speed of the light, right? That extra 0.009% really changes the relativistic factor. So it's an asymptotal relationship. Don't expect you to memorize this chart. I just want you to recognize how things change as you move closer and closer to the speed of light. Anything less than 10% of the speed of light is pretty much immeasurable. You might as well just call it 1 because it doesn't really matter too much. And if you're not too certain, just imagine yourself going to Edmonton. Oops, I didn't mean to click that. Imagine yourself going to Edmonton, put the speed of your car in here and just see what your relativistic factor is. And you can actually measure and calculate what your relativistic factor would be if you're driving to Edmonton. And you can figure out how much your time has actually changed. It's not very significant. In fact, some of you don't even have calculators that would be able to show the result of that. You need a lot of significant figures. Anyways, so the other consequence, not only time dilation is an issue, but you also have length contraction as you approach speeds near the speed of light. Now, if you watch Star Wars, you know that when they reach light speed, it looks like all the, oh, I should have grabbed an animation of that, but it looks like all of the stars elongate, if you will. That's not correct, not at all. It looks cool. It's really cool special effects. I'm not saying that's bad. It's just not correct whatsoever. So basically what happens as you reach speeds near the speed of light, your vessel starts to shrink. So if you can compare the 0.1 times the speed of light with the 0.7 versus the 0.9 versus the 0.9999, essentially you get shorter and shorter and shorter. Do notice that the overall width, if you will, and the height, well, this is not 3 dimensions, but the overall height of this little animation doesn't change. It's just the overall length. All right. And so the thought is if you actually can achieve the speed of light so that V is equal to C, technically the thought is that you no longer exist. You get so infinitesimally small, you disappear. Now, whether or not that's true, I'm not going to be able to say for sure, but that is one argument I've heard. Maybe talk to your professors when you get to university and get them to validate that, or definitely say that's just hogwash. They'll say it's hogwash. So if you're approaching at speeds near the speed of light, since the speed of light cannot vary, therefore time has to be relative, and also length is relative. So your length contraction equation is essentially L is equal to your original length, so your contracted length is equal to your original length divided by the relativistic factor. If you take into account what the relativistic factor is and the fact that it's in the denominator, basically looks like this. Okay, so LO will be our proper length. So for that, I'm going to bring out this bus question. So suppose you have a bus and it's about 15.5 meters long at rest. And suppose we have, don't ask how, we're on the magic school bus, if you will. I never watched that cartoon, I was a little too old for it, but just imagine yourself on that magic school bus. If it is going by at 45% of the speed of light, how long will we, who's that? Will I, let's say I, person who's not on the bus, because I never did watch that cartoon as a kid, because it didn't exist. Imagine me standing out here. Imagine you on the bus. How long will I say the bus is if it's going by me at 45% of the speed of light? Well, I just first figure out my Lorentz factor, my relativistic factor, just because I know there's a part 2 and a question 3 coming up. So I'm going to solve for this separately. Basically plug in my velocity, my speed. So 0.45 times the speed of light. So essentially it looks like this. Speed of light cancels out. Square my 0.45, I get that. 1 minus that, take the square root. All that divided by 1 gives me roughly 1.12 or 1.119. I don't actually remember what the number was. Okay, so that gives you my gamma factor. So if I use that gamma factor in my length contraction equation, I'm going to take my original length divided by that gamma factor, all right, 15.5 divided by 1.12, and I'm going to tell you that this bus, the magic school bus, is 13.8 meters in length. And that's how long I will measure it to be. You, let's imagine you inside the school bus. What is its length as observed by the people on the bus? What would you measure that to be? Well, you would kind of say that no, it's still 15.5, because once again, your frame of reference, your inertial frame of reference, you are at rest. Therefore, the bus is at rest. And it's the whole outside universe that is actually traveling at 45% of the speed of light. So that's a hard one to really wrap your head around. All right, so let's move on to question 3 then. So if the bus goes through a tunnel that has a proper length of 16 meters, what length do the people in the bus observe the tunnel to be? So random number 1 there. So here's my tunnel. Well, yes, it's just a rectangle, but go with me on this one. And here's the bus. So if it was going, slow, let's just say 15 meters per second, right? Roughly city speed limits. All right, we would just say, oh yeah, it goes through there, not a big deal, fits inside the tunnel, right? So it's going at really slow speeds. But you guys, oops, you guys are on the bus and you know that the outside world is traveling at 45% of the speed of light, because this is question 3. It's still related to the first 2. So from part 1, we determine at 45% of the speed of light, our gamma factor is 1.12, roughly. If we do our length contraction, we're talking about the whole universe is traveling at 45% of the speed of light. So therefore, we're looking for what you would measure that to be. So therefore, your tunnel, which is 16 meters when everything's at rest, divided by your gamma factor, the people in the bus would say that the tunnel is only 14.3 meters in length. So the entire universe actually contracts. And we've actually proven this to be true by just detecting muons that are coming down from our atmosphere. Muons have a half-life that is short enough that they shouldn't actually reach Earth's surface. But because they're traveling at speeds near the speed of light, the distance between the top of our atmosphere and the ground actually gets shorter. It shrinks, and so therefore those muons are actually able to hit the ground. So that's one of the ways we're actually able to test this out realistically. So if I were to draw a picture to it, the people on the bus would say, wait a tick, some of the bus, the whole bus doesn't fit inside, right? Some of the bus sticks out there, some of the bus sticks out there. So the whole bus does not fit inside the tunnel, because according to people on the bus, the tunnel is only 14.3 meters in length. So does the bus actually fit in the tunnel? Depends on who you ask. All right. Me, who's not in the school bus, would say that no, the bus doesn't fit inside the tunnel, because at the speed the bus is going at, the bus is only 13.8 meters long. So sorry, I would say it does fit in the tunnel, rather. Getting ahead of myself. Right, I would say it definitely fits inside of the tunnel, right? Tunnel 16 meters. I measure the bus to be 13.8 meters. Definitely fits inside the tunnel. You, on the other hand, said no, the tunnel is actually 14.3 meters long. Right? There's no way this bus, which is 15.5 meters to your reference inside the school bus, there's no way that would fit inside. They're both right, because it all comes down to their inertial frame of reference. So we can have a no and a yes and both be correct at the same time. So sometimes this kind of messes with people's heads. It takes a little bit to kind of accept it and wrap your head around inertial frame of references. So if two people are going at two completely different speeds, they will measure things differently. All right. So that's one of the consequences of special relativity. I'm going to stop the video here because I think this has gone on long enough. All right. Again, watch these 2 videos at a very minimum. Ideally, you should have paused this one and gone straight to those ones first, because then it would have made a bit more sense. But also read this textbook chapter, right? This is the type of topic that requires a little bit of reading on your part. So I'll stop this video here. Thanks for watching.